what's the probability of being able to get all of those joints when you assemble the microchip to that package substrate? You can imagine what's the probability of being able to get every one of those right. So there's a lot of research done in the assembly processes.
Hello and welcome to the Being an Engineer podcast. Today we're speaking with Hector Amador, a seasoned semiconductor R&D professional with over 13 years of experience at Intel Corporation. He has made groundbreaking contributions to IC and packaging design, reliability, manufacturing, and supply chain optimization. Notably, Hector holds a U.S. patent for innovations in high-capacity memory packages, and he has a track record of delivering cost-saving solutions and advanced industry-first capabilities in IC packaging and system integration. His expertise spans IC design rule ownership, and high-performance packaging engineering, making him a thought leader in the semiconductor space. Hector, thank you so much for being on the show today.
Thank you for having me.
So let's start with the same question that we always start with, which is, what made you decide to become an engineer?
I'd have to say a lot of science fiction. I used to read and watch as a kid, and originally I thought I wanted to be just a scientist. I think at the time as a young kid I didn't really understand the difference between a scientist and an engineer, but I was always the typical predilection amongst engineers, taking things apart, wanting to see what is inside, how does it work, drawing spaceships and cross sections. Once I saw in a book cross sections, I thought, "Ooh, how neat! Let me include those in some of my drawings." And so, come high school, I came to understand the difference. And because I do like to invent, draw, tinker, I realized I really wanted to be more of an engineer than just a pure sciences scientist. So, as everyone knows, engineers are they're scientists of the applied science variety.
What were some of the pictures that you drew growing up?
It was everything from a science fiction gun to a spacecraft to some kind of a special armored vehicle. It was all the kind of stuff that you normally enjoy as a kid. The adventure, the gadgets. Who didn't love either Batman or 007? Wanting to be able to design and get your hands on gadgets like that. So
definitely. I remember when I was probably 10 or so, I was really I'd kind of forgotten all about this until you mentioned it just now, but me and a friend of mine were really into drawing battleships with big guns on them and helicopters and fighter jets. And we would tape multiple printer pages together so we could create these giant drawings of, battleships and some big war out at sea.
Absolutely. That was cool.
Yeah. All right. Well, let's see. You are an expert in IC, and I think that acronym probably most people understand, but let's start there. What is IC packaging specifically? And maybe if you could just explain a little bit about that industry for us.
Sure. So when we say packaging, too often people think of cardboard boxes and styrofoam peanuts, and unfortunately that's not what that is. Though there are packaging engineers, and you stumble across positions like that when you're looking for what I do. Basically, everything that's part of an electronic device, let's say for example a CPU, everything other than the microchip, the silicon-based microchip, everything else would be considered part of a package. So it's what the microchip comes in. However, the functions of the package are much more complex. A package not only provides a way to interface the microchip, which is a very tight pitch between its electrical connections on the bottom, its solder bumps. It's a much tighter pitch than any kind of feature on the motherboard. So you not only have to provide sort of a crossover between that pitch and the pitch of features allowable on the motherboard, but the CPU package also takes the power and splits it into multiple voltage rails, different voltage levels. It conditions the power with discretes, like capacitors, to pull noise out of the power signals. It provides mechanical protection to the microchip, which is, of course, fragile and brittle. It provides a way to spread the heat and extract it out of the microchip and provide a protective interface to the system and whatever cooling solution the system would have. So the packaging does quite a bit, and it continues to be an area where innovation continues to be necessary, precisely because as microchips become more dense in terms of how closely their transistors are packed, as they become hotter, as they have to run with faster speeds, then anything and everything that intercepts electrical, thermal, or mechanical interactions between the outside world and the microchip, the package has to provide that interface without high parasitics, without undue impact to the function of the microchip.
You mentioned the pitch of soldering the microchip. This is exactly the kind of nerdy detail I think is super interesting. What is that pitch?
Well, from generation to generation, obviously, it's decreased. As you can imagine, I have to be somewhat careful in what I say, but let's just say industry standard now, and some of the more advanced semiconductor silicon nodes recipes and feature capabilities, you're down to 25 microns or even smaller between the solder bumps on the bottom of a microchip, and so you can be dealing with tens of thousands of tiny microscopic solder bumps that have to be connected to this electronic package, specifically what we call the package substrate, or the small high density fine feature circuit board that provides the interaction between the microchip and the motherboard.
Did you say tens of thousands of solder connections, little micro solder connections?
Depending on how large the chip is, whether it's server, whether it's a desktop or mobile, as in like a laptop, easily.
Okay. That's amazing. What is the process for depositing those microscopic copper pads?
Well, so as you know, there are a variety of processes for coming up with the microchip wafer, where multiple microchips are manufactured together. And you speak of the copper pads. Well, there are a variety of plating steps and/or of vapor deposition methods for putting metal on a microchip wafer. However, typically there's a solder interconnect. Yes, there are some more advanced methods where you're bonding copper to copper and applying heat and doing that, but more often than not, for the slightly older generations of microchips, you typically plate with some of the same equipment with which you process a wafer. You normally will do plating of tiny little bits of solder on each one of these openings at the bottom of the microchip, where you would have a pad. And again, different foundries use either aluminum or copper for that pad, but that solder provides a way of joining the microchip to the electronic package substrate by putting the two together through a reflow oven. So some solder or some flux paste on the package substrate is then bonded to the solder on the bottom of the microchip. You put them through a reflow oven, the solders meld, and you get an electrical connection. But each of those connections are actually quite delicate, and so ultimately you have to provide a kind of epoxy that you very carefully put underneath the microchip, bonding mechanically the microchip to that package substrate circuit board in order to provide the majority of the mechanical strength for joining the two. Sorry, I'm getting into a little too much detail.
No, this is so interesting. Tens of thousands of these things, and these microchips are small, right? I mean, what are they, like quarter of an inch or something?
Well, it depends on the market, depends on the function. Some can be quite small, some can be quite large, but certainly unless you're talking, commercial electronic devices, small microchips where you might have tens or hundreds of connections between the chip and the electronic package. The more modern microchips, you're talking at least thousands. And again, if you're talking a server or a GPU or an AI chip, it can be hundreds of thousands of connections.
Wow. That is amazing. I mean, this is all down at the microscopic level, right? It's not like you can see with the naked eye these connections. You're looking under a microscope
Very
to see these
difficult.
things.
Absolutely. And you can imagine what's the probability of being able to get all of those joints when you assemble the microchip to that package substrate? You can imagine what's the probability of being able to get every one of those right. So there's a lot of research done in the assembly processes in order
Amazing.
to ensure you get all those connections right.
Yeah, we could probably spend the entire hour just talking about that aspect and still not even really scratch the surface of it.
Absolutely.
All right. Well, let's move on to some broader questions. We talked about how you got interested in engineering. How did you first find your way into semiconductor?
Well, immediately after college, I got into mining tools, project engineering role, which was very exciting to me. I got to deal with things that take a lot of load, that drill through rock. They were these tricone drill and blast mining rock bits, and I got to oversee the manufacturing of them and the field testing and all that sort of thing. And the microprocessor employer was looking for someone that had 3D modeling, complex 3D modeling capabilities, that understood manufacturing well, and that was used to owning the overall project having to do with a product. So that's what got me in the door. I was wanting to do something a little more high tech after 3 years in mining tools, and so I found my way into the microprocessing field there. There's a lot of mechanical engineering involved, whether in the manufacturing processes, whether in modeling the behavior over its lifetime and making sure it's reliable, etc. There's a lot of thermal and structural engineering that goes into designing and producing a microchip. So you could stay lost in just the mechanical engineering aspects of that. But as time went on and I had to learn more things, I'm very happy that I got more and more sucked into the electrical as well, and the system architecture of the chip, and the architecture of the chip, and then the system architecture of the motherboard and the overall device. And so slowly just got sucked into a very, very large world. And I feel very blessed. I've gotten the opportunity to have a broad range of experiences over the years.
Yeah, wonderful. Well, you've worked on some like industry first type projects. Is there one that stands out to you that was particularly interesting or impactful that you could share with us?
Yes. Well, so looking back, everyone sees how there was a trend of microprocessors needing to get smaller and smaller and cooler so that the overall system doesn't overheat, etc. But the pace at which that needed to happen was under debate within my employer. And I remember working for one particular business group that was working on a device that was smaller than the typical laptop and was one of the markets we were exploring. And they really needed a very small, much smaller than what we had at the time, microprocessor. And I had to, as part of my role at that time, drive research and development, or technology development, as some people call it, of how are we going to make a microprocessor much, much smaller than we've ever done before. And I had to sort of push and drive, as I was tasked to do, getting all the right resources and people on board to really lift up every rock, look under every rock, and see what have we tried, what have we not tried. We've really got to get this thing smaller because there are a lot of market opportunities if we can make significant progress in that. And that particular, again, I have to be kind of careful what I say, but that particular microprocessor actually enabled the laptop manufacturer to significantly reduce the thickness of their laptop and launch a whole new product line, because we made it so much smaller in the planform area, the X and the Y, and thinner in the Z, and had to shrink everything related that sort of adds up in terms of manufacturing. Keep out zones, or the width of this, the width of that. Everything adds to the size. and we had to look under every rock and do a lot of new things we had never tried before in order to hit that goal and make the significant reduction we needed to. So that one I'm particularly proud of.
I can take a guess as to who that laptop manufacturer was.
Yes.
We'll leave it at that, but what a great bullet point to put on your resume, huh?
And in R&D, you have to do that. That's part of your job. I just was blessed enough to land into the R&D side of my employer, and so every day you were questioning everything. You were pushing, and so you just got used to that. At first, it's intimidating. Wow, how are we going to do that? But you realize, well, we somehow managed to come up with a solution before to lots of problems no one else has solved yet. So we'll figure out something this time too.
Yeah, it's amazing the secrets you can unlock once you point your brain at a very specific problem and focus intently on solving that problem.
Absolutely.
What do you think some of the most underappreciated technical skills are for engineers who are interested in being in the semiconductor industry?
Well, there are a number of skills that I really would have liked to have had when I came out of my bachelor's degree, and I really would like to see universities teach because it really helps with your abilities as an engineer, especially if you're going to go directly into a design role. And I'll be a little more specific now. So first and foremost, they don't teach tolerance analysis, tolerance stack-up analysis, and statistical tolerance analysis. So you look at an assembly of components and, well, what do I think is realistic in terms of how thick, how wide, all of these components together? What's that really going to give me for an envelope? If you're doing high volume manufacturing, you have to take that into consideration. You can't look at just the worst case or the extreme ends of what could be the pure summation stack of all these tolerances. And as you can imagine, you're throwing money away. You're increasing the demands of your product on a customer system if you can't be a little bit more judicious in your estimate of what's really realistic. So you look at distributions of your dimensions. You look at how those distributions add up, and just it's not that complicated. It's all really RMS, statistical RMS accumulation of tolerances in some particular direction. But if you're dealing with high volume manufacturing, the statistical or you look at the statistics for defects per million, for example, and that sort of thing. But really, doing an RMS study is really more realistic about what's likely to happen. And understanding, are you designing to 3 sigma or 4 sigma on either side of the mean, assuming a normal distribution and symmetrical distribution. So tolerance analysis, GD&T, something that's very popular amongst your podcasts. It's not something they teach in school, but you really need to understand that and gain competency in that to properly read a drawing and interpret what it really says and what it really requires of the manufacturer. Finite element analysis as well. Though I ultimately took some graduate courses that helped me gain a fair competency in that. That's not taught at the bachelor's degree. So you either have to get a master's degree or take some very targeted graduate courses in order to do that. And that one, if you'll give me a moment. Imagine, if you will, you're designing something complex, but in your bachelor's degree, you had solid mechanics. Maybe you're aware of Rourke's handbook of formulas that gives you some predetermined formulas for more complex geometries and how to apply your solid mechanics there. But unless you understand finite element method and some of the other continuum mechanics that goes with that, you really can't assess the goodness of your design if the geometry is complex without finite element method. And really coming out of your bachelor's degree or before you start some kind of a design role, you really need to have that under your belt so that the geometry doesn't throw you for a loop or keep you from being able to properly assess the capabilities of your design.
If I were in charge of university curriculum, that's the word I'm looking for. If I was in charge of the engineering curriculum at a university, what would you say to me? Like, what specific changes would you want me to make to better prepare students specifically for careers in semiconductor engineering?
I would definitely suggest a good emphasis on statistics, since you're saying semiconductor specifically, but really any high volume manufacturing industry. You have to understand your statistics so that you can look at stability, of what's coming out of your manufacturing process, repeatability and reproducibility, to design them experiments, to collect data, look at different permutations of your design. So statistics and a really firm grasp of that. Everyone had a statistics course, but ultimately high volume manufacturers, and specifically semiconductors, at least from my experience, end up really needing, they make a lot of statistically based decisions. You go and you get statistically significant data because you're trying to make assessments and decisions based on a certain number of samples, but you're trying to make conclusions and decisions about what would ultimately be the overall population. And if you don't have a good, firm grasp of statistics, you don't know how to do that. So definitely more statistics. I would say probably also things like having a lot more practical, hands-on experience with what you learn. I know in my bachelor's degree, they lumped all of our lab experience into 2 classes, and these often came in the curriculum semesters after you've taken the academic course. And so really, I think if for every class where you think you want to have the students practice some lab exercises, those really should, in my humble opinion, occur during the same semester that you're taking that course, because that really emphasizes the material and makes it stick in your mind if you get to play with the phenomena in the lab as you're learning it. Having to play with it semesters later doesn't add to really making that information become part of your psychological schema of the world. And it really sort of becomes a very unsettling exercise of now you have to go back and review exactly what you need for this lab, and you're sort of cramming all these lab exercises together into 2 courses.
That's a great suggestion. I like to say learning or doing is better than learning about doing.
Absolutely. There needs to be more hands-on, because I mean, that's what engineers love to do. So why would you have them spend the vast majority of their time in a lecture hall listening to a professor? You want to get your hands dirty. So
I agree.
And I'd also mention again, I was kind of glancing through my notes, but I'll go off of memory. I was very happy that because I had to pay my way through school, that I found my way and sought internships during college, but that gave me hands-on experience. Not only doing some engineering projects and calculations, but I also got to see what the engineers in the office were doing. That gave me a better sense of, I really want to do this for a living. But in an office environment like that, you also learn some professionalism. You learn how to function in a corporate environment. And if you don't have experience in some internships before you graduate from college, that seems to be very unsettling for some graduates. I've heard the corporations complain. If we get a kid straight out of school and he's had no work experience, and certainly no corporate work experience, they seem like fish out of water, and they take time to adjust to the corporate environment and the expectations, even some of the unspoken rules about how to conduct yourself professionally. And so that's a soft skill that can really help your career, that really should be somehow taught to some degree, I think, in your undergraduate degrees, for sure.
Yeah, if there was one piece of advice that I could give to students specifically, it would be get more hands-on experience before you start working professionally as an engineer. And having an internship is just the best way to do that.
Absolutely.
Let me take a very short break here and share with everyone that the Being an Engineer podcast is brought to you by Pipeline Design and Engineering, where we don't design pipelines, but we do help companies develop advanced manufacturing processes, automated machines, and custom fixtures, complemented with product design and R&D services. Learn more at teampipeline.us. The podcast is also sponsored by The Wave, an online platform of free tools, education, and community for engineers. Learn more at thewave.engineer. Today we are privileged to be speaking with Hector Amador. So Hector, let's see, let's go back into the wonderful wide world of semiconductors. And with semiconductor is pretty huge right now, especially with the proliferation of AI. That's really skyrocketed the semiconductor industry. How are you staying ahead of emerging trends to make sure your skill set remains relevant?
I definitely encourage people to be a part of their relevant professional associations. Especially, for example, for semiconductors, that would be IEEE, the Institute of Electrical and Electronics Engineering. Not only if you subscribe to their journals and have access to academic papers that are put out, industry academic papers through there, and attending conferences, classes, meetings, you not only network, but you get an idea of what's going on outside of your own company, but within other companies and in the industry as a whole. So that's definitely one major way to keep up with things. And subscribe to other journals. Be informed of changes in standards in your industry, because those affect everyone in that industry. Things like JEDEC, being aware of and having access to JEDEC standards, which govern a lot of certain things that industry participants like to settle on to create more fungibility between devices or manufacturing of devices. Certain standards are established by JEDEC, and you need to know what those standards are, especially if a customer goes, well, I want this to be JEDEC compliant. You have to know what that means. So participating in those sorts of standard making bodies, ANSI, some of the ASME, some of the mill standards, all that sort of thing helps you understand, having a pulse on that helps you understand what's changing in your industry and those things you need to be aware of.
Staying up to date with the latest and greatest information relevant to your industry often is largely valuable because it allows you to optimize costs in your processes, right? Every business has to be profitable or it ceases to become a business. And so cost optimization is a big deal in the industry. You have been able to achieve some pretty significant success when it comes to cost reductions through process optimization. Is there a particular experience that you can share to help communicate kind of your process for identifying opportunities for cost savings?
Well, certainly it's a team effort. And I want to say that in my employer, in the microprocessing industry, we had teams of folks that were really, really great material scientists, looking at new materials, understanding what are the trends that we need to be aware of in, let's say, for example, some of the polymers that go into that packaged substrate circuit board. You know, you want to have better electrical capabilities, so lower loss. Lower loss tangents, and maybe you want it to have a higher glass transition temperature, so it doesn't soften prematurely from where you might want to be operating. These guys know what sorts of things that we want is in terms of improvement for materials. So not only are they investigating new materials, but lots of engineers can go out and survey either material suppliers, look at their websites, look at what's going on with their new materials, or become more knowledgeable yourself of materials that already exist in the market and go, well, if I chose this, what are the differences? How is that going to affect my structural or my thermal performance of my microprocessor? And so, again, you have to question everything, including your material choices. Those are very, very significant as well.
Yeah. Okay.
You asked about a particular instance. So one particular project where we were producing these chipsets, these things that help the CPU on the motherboard. This particular chipset was for a high performance interface, one that's particularly fast, and incidentally was an interface jointly developed between that laptop manufacturer we were talking about and my employer. So as they are producing product after product within a product family, the business customer inside our company came and said, well, look, we need to cut the cost of this thing in half. And obviously that is at first seemed very daunting, but you think to yourself, okay, well, let's look at the major, if you were to look at histogram and what are the contributors of the cost, you'd say, well, what are the heavy hitting contributors to the cost? And let's look at what we can do to reduce those or replace those with something more cost effective. So size is certainly one thing. for that circuit board, the smaller you can make it in X and Y, and the lower the number of layers that it uses, the less expensive it can be.
Is that just because it's less material costs?
Yes, precisely. So, and again, these things are usually produced depending on what kind of package substrate circuit board it is. They can either be produced in large panels individually and later are singulated out of that panel, or they can be part of a strip that's processed that has multiple circuit boards in it, and then they're singulated from that strip. So depending on what technology, what materials you're using, and how it's manufactured, those are the things that affect the cost. So making the circuit board smaller, making it have fewer layers, which requires you to play with the electricals and play with the mechanicals as well. If it's thinner, it's more likely to warp. Well, how do you compensate for that when you need the right kind of rigidity, especially when you're trying to mount it to a motherboard? It needs to be at that temperature as flat as possible, and you want it to be matching any warpage of the motherboard ideally. But most of all, you want it as flat as possible at that reflow temperature. And if you're going thinner, well, that becomes potentially a problem. So you're constantly balancing material choice, the number of layers, the size of the package. You might use something, for example, on the top of the package that helps stiffen it. People who've worked in the semiconductor industry have seen different electronic device manufacturers using a metallic stiffener on the outer perimeter of the package. You can play with the thickness of the silicon. Well, you have a CTE mismatch there between the organic polymer substrate package and the die, but sometimes you can get some stiffening benefit by using a slightly thicker microchip. So you have to play with all that to not only go smaller and cheaper, but still get a viable product that has a good reliability through its life.
Okay. Clearly, you're an expert in your field of semiconductor.
I mean, experienced. I don't know.
Yeah.
I don't feel comfortable with the word expert. Sorry.
With that, I guess, position in the field, what are some of the challenges or obstacles that you foresee in semiconductor over the next 5 to 10 years?
Well, we're definitely at some point in the very near future going to think outside the box quite a bit. Everyone's aware of Moore's Law. Everyone's aware of, as you start packing these transistors closer and closer together, the power demands increase, the necessity to cool increases, and those become very difficult challenges to maintain. And so eventually you're going to hit some kind of a physical limit. You're going to start dealing with dimensions that are so small. You're talking about layers that might be only a few atoms thick. You're going to hit some kind of an issue. So you either have to have a big jump in your computing capability, which some people are doing looking in quantum computing, to be able to get a lot more output and faster results within a certain space. Or we're going to have to fundamentally change what we do in terms of how we build microprocessors. Now, I'll cite an example that I think is an exciting new field that certainly has not been exhausted for its potential. Already, some people have been researching ways in which to store information at the molecular level. Now, again, there'll be a stretch from storage, information storage versus computing and behavior of components like transistors. However, with the size of molecular devices, with nanotechnology, that might hold promise. And again, that's just some conjecture on my part, but in terms of the possibility of looking at a completely different way of building microprocessors in order to overcome the size limits, in order to overcome some of the physics challenges of cramming a lot of power and a lot of heat, relatively speaking, into successively smaller and smaller areas. So we're going to have to definitely think outside the box, and it's those kinds of revolutionary technologies that will give us that headroom and that margin going forward in the future.
I'm curious what problem you would want to focus on and how you would attack it if it was up to you. So let's say I'm giving you $100 billion and saying, go do the next big thing in semiconductor. What would you choose to spend that money on? And you're more importantly, what would you choose to spend your time doing?
I would probably want to focus on quantum quantum computing. That seems to be the next most reasonable area of development, where you're increasing multifold the amount of data you can represent and computing that you can do, um, for the same kind of, how would I put this? It gives you an economy of scale over traditional microprocessors. Right now, though, what you're doing takes a lot more space. Quantum computing devices don't have the device density that current microprocessors have. So there's got to be a lot of work in miniaturizing that technology, and that's going to involve different manufacturing processes, different materials, and different ways of interacting with those devices, because obviously quantum computing not only has very different boundary conditions, but very different logistics. So I see that as probably the most promising next technology, where if we can apply the right work, energy, in terms of design, materials, manufacturing processes, I think that holds the next big benefit.
Terrific. Okay, couple more questions, and then we'll start wrapping things up here. For you've held some leadership positions, pretty high level roles, managing teams and taking ownership of entire programs. For engineers who are interested in stepping into that sort of role, what kinds of mindset shifts or skill sets do you think are most important for their success?
Well, strangely enough, when engineers think about the skills they need, they don't often first think of leadership methods or psychology. And if you're going to be asked to inspire people and lead and sort of get people all going in the right direction, I found it very helpful to study psychology and leadership methods and different ways of getting people to buy in to a common goal. There's one particular Harvard professor that put out a leadership book, and I'm sorry I don't have it handy here with me, but one of the key things that he stated, and again, it's quite popular book and one I enjoyed quite a bit, was a leader has to come up with the vision and then inspire others to buy into that vision. And again, that's not a manager who just handles and oversees getting certain lists of tasks done. This is a person who has to drive a direction and get everyone going in that direction. And leadership is a complex thing, and it does involve psychology. So understanding how to motivate people, how to work with a team, those are very, very important skills that become more and more necessary as you deal with larger and larger projects and teams. Some other skills I would say have to do with broadening as well as deepening your knowledge of the people that you work with. Just a very general example, a number of times I led a program. I was a packaging program manager. And so I would be overseeing a family of products. I didn't at that time have anyone reporting directly to me. I was not their manager, but I still needed to oversee and direct the activities of a number of different people from functional areas, reliability, thermomechanical simulation. I've done some of that myself. People managing the supplier, people doing the electrical simulation and the layout, the design. These people are matrixed to you from their respective organizations. They're not your employees, but you still have to find a way to get them to work together properly. They're often from different cultures, different time zones, and you have a complex set of things that you have to keep track of and leverage the capabilities and the skills of all these people. Of course, like I said, it's a team effort, but you have to keep an eye on the big picture as well as get down into the nitty-gritty details if there's something that's acting like an obstacle or stopping you. So as you learn and grow, You have to not only learn more and more about what the people who are adjacent to you, who take your work, when you're an individual contributor, learn more and more about how your work affects others, how their work affects yours, and then you start to have this higher level knowledge of what's going on so that you can ultimately lead a team because you understand what they each need. You can see potential conflicts or disruptions between different efforts, and you end up having the experience and the I say vision, I should say, being able to proactively predict problems and head them off in advance.
I love that you talked about psychology. I've always thought psychology was so interesting. I've specifically, I really think, behavioral economics, behavioral psychology is just fascinating. I've read a few books about that from different, authors and researchers. What I'm curious to ask you, what is one of your favorite, most interesting, most impactful psychological principles that you've been able to use in your professional career?
So I'm a big advocate of the Dale Carnegie courses. I managed to take some, and one in particular that really had a big impact, really brought a lot of skills to bear, is one called Making Friends and Influencing People. And that's sort of an innocuous sounding title, but there's a lot of great information in there. And if I could summarize everything taught in there and boil it down to maybe one statement, it's seek a win-win solution and truly listen to and empathize with the issues of someone that you think might be counteracting or working against you, or who has some need that you think perhaps is conflicting or interfering with yours. Obviously, there's always some healthy tension in a system. There's always going to be overlap between, well, the quality and reliability person needs this, but the mechanical design person needs that. If you look at really understanding what the other person needs and find that win-win solution, not only does it help you better manage the team to a successful convergence and conclusion, but it goes a long way to building trust and close interaction within a team.
How to Win Friends and Influence People. I remember reading that back when I was in high school, and it was, how do I say this? Kind of a foundational set of principles for me back then. Wonderful book. Another one I've read more recently about similar topics is by an author named Robert Cialdini, who is a professor here at ASU, Arizona State University. Actually got to go to lunch with him about a year ago. That was pretty cool. Anyway, he wrote a few books, one in particular called Influence, The Psychology of Persuasion. And that one was really wonderful. So many real world tested principles that he learned, all about how to influence people, not manipulate people maliciously, certainly not. In fact, he speaks a lot about ethical influence, but how to influence people to produce the best outcomes for everyone. So anyway, I'll add that to the mix for a book recommendation.
And on that topic, if you don't mind, certainly, even as a first level manager, that's an art and a science. It's not something you can kind of do successfully by the seat of your pants. And so I certainly have to attribute a lot of the really good management training that my employer provided because they really want to make their managers successful. A lot of that was also very helpful and based on some very time-tested concepts. So there are a variety of things there. And I certainly encourage employers and individuals to look into and take those management courses because they're not trivial. It's not these are non-obvious things.
Yeah, wonderful. Well, last question here. What is one thing that you have done to accelerate the speed of engineering?
Well, so, and I wanted to make a specific or cite a specific example, and that is really looking at ways to increase efficiency. A lot of times there are a number of tasks that you know you're going to do, and looking for ways to take time or complexity or the opportunity for error. Whatever you can do in those avenues certainly can help speed up your work and make you more efficient. And in that particular way, at least chronologically, increase the speed of engineering. So I'm all about creating templates after doing one project, creating templates, spreadsheets, formula-based algorithms, any kind of automation, some little subroutine you can write. I believe once you've got a good algorithm and you've got well-proven results, why do that work over and over again? Why not leverage, the automation that modern technology provides in order to come up with a faster and more robust process?
Here's a question for you. I'm curious to hear what you say about this. I agree 100%. We should be leveraging, capitalizing on processes that we've already developed. Let's not reinvent the wheel. Yet, many engineers, that's what they really love doing, is inventing the wheel, right? Even when a wheel already exists. Is there a balance that you've found to allow engineers to scratch that itch of creating, inventing, while still steering them towards the path of efficiency, not duplicating work, etc.?
I've seen success with making sure that a person who's going to be tasked with something like that, where they need to be innovative, for example, I've seen great success with making sure they already understand what has already been done, so they're not needlessly, again, reinventing the wheel. Teaching them what already has been done, but encourage them to question, well, how can each of these methods or algorithms or whatever be made better? Because too often, indeed, if you just look at what other people have done, you might fall into this trap of a sort of groove. Oh, well, this is how we've always done it. Well, learn what's been done so that you have that as a foundation to leverage, but then go back in and question everything, because I think many times certain stones, metaphorical stones, have not been turned over. And if you don't go back through the work that has been done, there are often some nuggets, some opportunities for improvement that are left behind in the rush of getting this project done or that project done. And if you think about it, sometimes there have been academic papers I've seen that go back and question something and find an exception, a flaw, a refinement of some body of knowledge, because too often everyone builds on what everyone else has done. Everyone wants to build the Tower of Babel, if you will. They want to build on top of what the last guy's done, and there's not enough peer review sometimes or enough scrutiny. And, well, does that need to be tweaked a little bit? Is that not quite right? And I think going back and questioning and retesting what has been done before helps you look for those untapped areas for improvement and refinement.
Definitely. Hector, thank you so much for sharing your precious, valuable time with us today. What a wealth of information and knowledge you have shared, insight with us. How can people get in touch with you?
I'm on LinkedIn, and my profile is the usual preface with Hector-Amador 777. And other contact information is available through my LinkedIn profile.
Terrific. We'll put a link to that in the show notes as well. Before we sign off, is there anything else that you think we should discuss that we haven't hit on yet?
There's a lot, but I simply want to thank you for the opportunity to be on the podcast. I'm a fan of it already, and a number of other sessions that you've had. So I feel very fortunate to have had a chance to participate.
Thank you so much, Hector. That's very kind of you to say. I appreciate you being on the show.
Thank you so much.
I'm Aaron Moncur, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing advanced manufacturing processes, automated machines, and custom fixtures, complemented with product design and R&D services, visit us at teampipeline.us. To join a vibrant community of engineers online, visit thewave.engineer. Thank you for listening.